There's most of you braved it out today and did go Deer Woods, so thank you for showing up to class. I'm going to reward you with some extra clicker questions. They're I'm here today questions. Just some thing I want to talk about the last unit that we're doing. So it's going to cover chapter 8, 9, and 10. 10, I told you, is really short, but there's practically no math involved with this. So if you want a chapter where you can study and memorize notes, there's less critical thinking on this unit than there, especially there were the last two tests. It's an opportunity to bring your grade up. So just, and the reason I tell you that is you plan going the last week. Everybody's last week of class, practically every class is going to be a test or a major assignment to do. And then you're going to have the finals following up. You weigh as you figure out how to study, where to spend your time. You weigh out where you're going to invest your time in. That's part of what you learn how to do is you're learning how to study. So this is one of the things that you can study ahead on. So you can, as we finish the notes, just review that material, go through it thoroughly, write up a set of review notes, and then you can be good for the next one. You don't have to study it all right in the last week or the days that we're going to take the test. We'll probably take that test on Tuesday. I'll get it back to you the next day. We'll probably cover some more material, but I like to spend the last day of class doing a review of filing 10. So, but I want you to certainly have your test back. It doesn't matter if I don't cover, exam 4 doesn't cover everything that's going to be in the material, but just have that idea. Anyway, so here we are back in chapter 8. We'll probably finish that today. If not, we'll become very, very close to it. Tomorrow we will not do lab, but we'll do the chapter 8 problems. If I like a few slides today, we'll finish those up. Your chapter, Mastering Chemistry for chapter 8 is due tomorrow night. Then we're also going to start chapter 9. So I would rather go ahead and get through our material, spend more time review. If we get to take a day off at the end of the semester, then it's study. Okay, but I want to make sure we have time to cover the material we need to cover. So the last thing we're talking about is these trends that we have in terms of size, atomic radius, and we were looking in particular the main group elements. So the general trends that we have is that atomic radius increases as you go down the periodic table. So here's looking at the alkali metals. So here's lithium, and if you go down, the next thing on the 1A family, there's sodium and potassium, rubidium, and cesium. It's just slightly getting larger and larger as you go down the table. Okay, it's not that big of a jump. And the other thing that we said is they get smaller as you go from left to right across any particular period. And that's the trend that we said that goes like this. And once you fill the noble gas, typically the noble gas is the smallest thing in that period, then it jumps up. It's the next layer of the onion. Okay, the next shell of electrons starting. So all of these electrons are in one shell. All of these electrons are in one shell. All of these guys are in one shell, etc. So as you go down the periodic table, the valence electrons are farther from the nucleus. That's the next shell, the next layer. So every one of these alkali metals represent a different layer. The effective nuclear charge, however, remains fairly similar to one another because the charges of the core electrons shield out the most of the nuclear charge, and the only thing you see is the outside valence electron sees that partial charge. Now, when we look at what happens with electron configuration and the main group elements and the electrons they tend to form, what happens is that we know that metals have the characteristic that they're going to lose electrons off. When they do, they form valence, or they form cations, so positively charged things. And the electrons are lost first from the valence shell. The outermost electrons are the ones that are given off first. And that's almost always the trend that we see. So if I look at aluminum in the 3A family, it has 3 valence electrons. So those 3 valence electrons are in the 3s. There's 2 there, and there's 1 in the p. But if it reacts with something and loses electrons off, so it's oxidized, when it loses electrons off, it's going to lose electrons to be like the nearest noble gas. So aluminum's here at 13. If it loses all 3 electrons, it becomes like neon.
So when these three electrons depart in the system, so these three electrons are lost off, what I'm left with is the 3+ cation, and it has an electron configuration of 1s2, 2s2, 2p6, but we get to the point where it's the magic 8, what we call the octet. Okay, that's the stability that atoms are trying to react to reach, both anions or cations. They're trying to get the 8 electrons in their valence shell. That's a stable form, and aluminum 3+ is a very, very stable species once it loses those off. All right, so if we look at some general things that we can say about gaining and losing electrons, transition metals are a little bit more complicated. And they're them for themselves because of the variability that happens with them. Usually the first electrons removed are typically going to be the valence electrons, even though they may not have been the ones that were last added. We looked at some examples about how when electrons add, atoms will do half fills and do partial fills because there's some more stability at that. But when they lose them off, they're going to be lost from the valence shell first. Okay, and it may be that the valence shell is further removed than some of the other sublevels. That's the way that things lose them off. So here's an example of the iron atom. So iron Fe has 2 valence electrons with it. So its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. So here are the 2 valence electrons. All right, so with that, when it reacts, and it's a metal, so it's going to lose electrons off. When it loses electrons off, the first ones it loses are its valence electrons. So what happens most commonly with iron, when iron loses 2 electrons off, it forms the iron 2+ cation, which is very stable. Okay? What happens, you lose those 2 4s electrons off, so pencil back. So this is minus the 2 4s electrons. And this is a stable form of iron. And if we look at iron in nature, so when we dig iron up in the ground, we don't ever find elemental iron. The way that we've used it in the industrial age, we get iron ore. And iron ore is a combination of rusts of different types. It's iron oxides. Some of the iron that we see is the iron 2+. But also what can happen with iron is then it can also lose one of the 3d electrons, because this 6 gives me the odd man. So if I look at what happens when iron forms the 2+. So the first 2 electrons it left off were those ones that were lost out of the 4s. These guys were removed, but still it's left with 6 electrons in the 3d. And that's stable, but the other thing that can occur is that it can react to lose off the 7th electron. And what happens, it loses the 7th electron, this electron gets ejected off, or it's lost to something else in a redox reaction. So now what you have is one where you have a half-filled orbital. There's 1 in there. Half-filled is stability. So which one is it going to be the most stable? Well, it's almost a coin flip. So if you take iron, and if you look at things that we've always observed, if you have a piece of metal that's shining metal, and you expose it to some water in the air, and you let it sit outside a couple of years, it's going to rust, form iron oxide on the surface. But the mixture of iron oxide that it forms just really varies on the stability of it. So it forms a mixture of these 2. So where this represents the iron 2+, and this forms the iron 3+. Most of the times when you look at iron or rust on the surface, you'll see some of the rust that's a powdery orange, and that's the 2+2 ratio, and you'll see some that's more of a deep red, The more deep red is the Fe2O3. But it's usually a combination of them. It's odd in the way that occurs. They're so similar in terms of stability. Most of the time, it's roughly a 50-50 mixture that you see. Okay, but when you start doing chemistry with it, the most stable one in chemistry-wise is this configuration. But it takes some energy to pluck this other electron off, so a lot of times it's perfectly happy staying in this space. So this is the most stable overall. But in nature, it's typically a 50-50 mix or so. Sometimes it's slightly favored to this guy. Over the natural processes, the iron ore that we find, so this is, I'd say, in rust. When we dig up iron ore, it becomes a little bit more favored in terms of the Fe2O3. It's about a 1-to-3, but it actually depends on the piece of ore that you dig up. Where does that field at? The two things are very similar in terms of stability, and that's where it makes it kind of complex with transition elements. It's not always one or the other. It's both sometimes. Okay, and that's it's the nature of it. All right, one of the properties that we take advantage of in terms of especially transition elements are their characteristics that they can have magnetic properties associated with it, both the neutral atoms as well as the ions themselves. And the electron configurations that result in unpaired electrons, and it doesn't matter if it's one electron, or in the case of iron-3, if it's got 5 electrons, that means that it's going to have a net magnetic field, and if that's the case, we call that paramagnetism, and that means it's going to be attracted to a magnetic field. When you have all the electrons paired up, so meaning no free electrons that are unpaired, it has a 0 magnetic field, and that's called dimagnetism, and those are things that are not attracted to a magnet. And it's very so slight, but they're actually repelled a very, very small amount by a magnetic field. So if everybody's taking a magnet and you've touched different things, does it stick to it or not? Anything it sticks to is paramagnetic. That means it has some electrons that are not paired up. If it's like aluminum, a magnet doesn't stick to aluminum, that means that it's dimagnetic. Make sure you understand the difference in the two. So what causes something to be magnetic, and is it paramagnetic or dimagnetic with the definition? Okay, so if we look at what happens with the sizes, it's a little bit different when we start looking at ions. Now, we talked about the size of neutral atoms at the start of the class. When you lose or gain electrons, now you have an ion. The trends in the radiuses are a little bit different. So what happens is that we know that ions formed in the same group typically have the same charge. So things in the 1A family are going to form 1+, 2+, 2A family, -1, 7A, -2, 6A, etc. So what happens is the size of an ion increases as you go down the column. Okay, more shells to the onion, if you want to think about it. So a higher valence shell, the larger it's going to be. And now what changes depends on whether it's an anion or cation. So what happens with cations are smaller than the neutral atom, and anions are larger than the neutral atom. Okay, so let's think about the why of that right quick. So let's choose a lithium atom. Okay, a lithium atom is a +3. All right, so here is the nucleus, a +3, and you've got 2 electrons here in the 1s shell. You got an electron spinning around here, and we got another one somewhere. And then you've got this last electron. If it's lithium neutral, you've got one more electron in the 2s shell. So you've got another electron spinning around here. So you've got this shielding of this, the first two. So this electron sees approximately a +1 charge when it looks in. Right? But whenever I have lithium 0, or lithium +1, once it's lost its electron off, so now I've got the +3 in the nucleus, and I've lost the electrons off, so all I have are the electrons that are in the 1s shell, and there's just 2 of them. So both of these electrons experience the full +3 of that charge, and with Coulomb's law, the greater the charge, the greater the Q, the greater the force. It's pulling those things in tighter and tighter. So the result is that the lithium neutral metal would be big. The lithium ion is going to be significantly smaller. Okay, that's the trend that we see. Now the opposite's true with anions. If I gain electrons and put more electrons in there, the attraction between those electrons becomes weaker because I'm trading that same nuclear charge among more electrons. So that electron clad spreads out and gets larger. Okay, so that's the trend that we have. Now we've got some general terms that we can say is that cations are most commonly smaller than anions. The only exceptions are some of the two biggest cations, rubidium and cesium. So the bottom left, those are our big guys. They're about the same size as fluorine or O2. And if you go anything, these are the smallest of the anions. Anything else bigger than that, the anions is bigger than the cations. Okay? So the larger the positive charge, the smaller a cation is. So if I look at something that has a +1, a +2, or a +3, a +3 charge means it's lost 3 electrons off. That nucleus is just pulling tighter with those electrons that are left. So it's going to be greater. This becomes more and more of a factor that makes things smaller. And that's especially true for things that are isoelectronic. And that means they have the same electron configuration. So if I look at an example, what's something that isoelectronic? So if I look at the aluminum 3+, we said when aluminum lost its electrons off, it lost 3 electrons. It had a noble shell length of electrons like neon. Okay, if I look at magnesium 3+, it loses 2 electrons. It also looks like neon. And when sodium loses an electron off, it looks like neon. They all have 1s2, 2s2, 2p6 in electrons, 10 electrons left. So those are a group of species that are isoelectronic. So what happens on those 3 is we get to the larger charge. Aluminum 3+ is much, much smaller than sodium in terms of size because the electrons are being sucked in by the nucleus more and more. The opposite is true when you go to anions. The larger the negative charge, the larger the ion becomes for isoelectronic species. So more electrons you got in there, the weaker the interaction, the bigger and bigger that shell becomes. So these are kind of summarized in a couple of trends here. Here are cations. So in gray are the neutral metals on all of these, right? And then what happens in the red, so I like that in a different color, represents the size of the ion. In some cases, you'll look at this top row, it's a very dramatic change, especially when you go to something like boron. The boron 3+ cation is its volume is less than 15% of the volume of the neutral boron atom. Because of that 3+ charge now sucking the electrons in, it's tiny compared to the neutral atom. So if you look at all these things, what you see is that the cation in every case is smaller than the anion, or the neutral atom. So that's our trend that we always see with these guys, is that cation is smaller than neutral atom.
Yeah, with like biology, they would always say that the cations break down stuff, so how would it do that?
What do you mean breakdown?
I don't know. They just said that they were used to break down. I think she's talking about yeah.
Okay, that's a process of enzymes.
Mm-hmm.
Okay, it's not individual cations. Even though it shares the start of the word, different. It's not a chemical entity. Okay. All right. So if we look at what happens anions, it's exactly the opposite. So here with the anions, we have the neutral element here in the gray colors again, and then we looked at the size of the ion represented with the blues. Okay, and you'll see that some of these things that, like an iodide, it gets considerably larger. Okay, but it's not getting as larger percentage-wise as what fluorine is. So its radius went from 72 to 136. It almost doubled. Okay, if you look at what happens with oxygen, 73 versus 140, it's almost double. Okay, the electron clouds really jumped out in size. So in the next chapter, and especially in chapter 10, we're going to start putting the atoms together in 3D.
So now size becomes a factor because you have things like you can get a big ball and a small ball, and you get things space limited. They can't get close to one another. It's called steric hindrance. It's the term we use to describe it. But the size of the individual atoms makes a difference, or the ions of what can bind to it. Yep.
Why do they get, the radiuses get larger in the anions? Is it just because there's...
Okay, so let's, we talked about with the cations, let's do an example with the anions. Let's do chlorines. So chlorine's electron configuration is that it's valence shell. It's got 17 protons in the core. Okay, so it's a plus 17 charge for the nucleus. And then it has these well, I'm going to just call them core electrons. So how many core electrons does it have? You'll have a test question like this. So it's got 17 electrons total if it's neutral. How many are valence electrons? It's 7A family, 7 valence electrons. So there are 7 valence electrons here. Okay, so 7 electrons in the valence shell. Right? So that means that there were 10 core electrons here. So when it picks an electron up and it converts to the chloride ion, okay, so the black represents, what I've done in black here represents the chloride neutral. If it picks up an electron, becomes the chlorine -1, now that extra electron becomes in the 8th shell. So when it's looking in, its effective nuclear charge that it sees is it's 7 of these are shielded, it sees approximately a +7. So it's 7 and 7 versus an 8 and 7. And when you have 8 there, that charge, if you think about, the way I think about it is, okay, it's seeing a 7 positive charge, and it's distributing that 7 charge combined against, count my electrons, against 7 electrons. So they all are sharing a 7th of that charge effectively. But now when I throw an 8th electron in here, okay, when I get to the 8th electron, now they're splitting it by an 8th. And as it gets weaker, the electrons get further and further out. They're not drawn in as much. Okay? All right, there's a good explanation in the textbook. You'll look at the notes. It has some figures with it, compared to several different ions. I encourage you to take a look to see that further. Okay, the next thing we want to look at is ionization energy. So what happens when you start plucking an electron off? So ionization energy is described as the minimum energy removed or needed to remove an electron from an atom or an ion. You've got an electron here, or got an atom here with some electrons around it. So you got a positively charged nucleus, whatever that charge is. There's an electron circling it. What energy is required to pull that electron completely off? Right? And what's described as pulling it completely off, and it's described as when the potential energy difference between these two things goes to 0. That's when it's effectively removed. Because I can take an electron and move it out to a further shell, all right, different layers of the onions, and it's still attached. That's what happens when we excite an electron or an atom. An electron jumps from a lower level to a higher energy level, as we talked about. So what's happening now is that I'm plucking them completely off of the atom. So we describe this in terms of being a gas state, and it's always an endothermic process. So it absorbs energy to pull that electron away. The valence electrons are going to be the easiest one to remove. So they have the lowest ionization energy, and they're usually described progressively. So you take something like a metal atom, you add some energy to it. This is the first ionization energy. And you add enough energy that you pluck this first electron off. But now what happens is that I've got a M+1 cation. And we said cations are smaller. And the reason they're smaller is because the electrons are being pulled closer and closer to the nucleus. So what happens is to pull the second electron off, it's going to take more energy to pluck this second electron off because of the +1 charge that's there. So what we see is the second ionization energy is almost always progressively more. Okay, it takes more energy to pull the second electron off than it does in the first. So there's some trends that we have with what these ionization energies are going to be. And it comes down to the effective nuclear charge, how much shielding is going on. The larger the effective nuclear charge, the more energy it takes to pluck that electron off. Okay, if we look at something that's further away in the outer shells, the less energy it takes to remove it. Because it's already at a reduced potential energy, because of distance, potential energy is related to the inverse electrostatic potential energy is related to the inverse square of the distance. So you get close, it's a strong pull. We get further and further away, it's a weaker pull. And you get way out here, it breaks completely off in terms of pull. So the trends we have for the first ionization energy is they get smaller as you go down the periodic table. The bigger the shells, the more layers to the onion. Okay? Because the valence electron's further to the nucleus. And generally, here's the trick word, not always, but generally it increases as you go across the period. Go left to right, it gets larger. And the reason there is because the effective nuclear charge becomes greater. All right. Here's another table that's showing what's occurring here. All right. This is what we call the sawtooth pattern that we see. So we've got this pattern that's occurring that's a sawtooth. And then we see another pattern here that's associated with this. So those sawtooths that we call them are where you have stability in the system. Okay? There's extra stability here if we think about where these electrons are. So this is the electron configuration of this first element. So this is lithium. Lithium has 3 electrons, 1s2, 2s1. Okay? So it'll get rid of that first electron easy because that makes it like a noble gas. And then I go to the next element. So go to the right of the periodic table 1. I'm at beryllium. So it's a 1s2, 2s2. But now the fact that this one's full of stability. So it takes quite a bit more energy to pluck the next electron off. All right, but if I go to the next one, if I go to the next element across the periodic table, and if I go to boron, element 5, so here is boron. Boron's 1s2, 2s2. Okay, so now I'm putting an electron in the P. It's easy to get rid of that electron, because if it gets rid of it, now it has a full pair underneath it. So it actually is a little bit lower energy here. It doesn't always go down. Sometimes it went down just a little bit, or it doesn't always increase going left to right. That's the reason that generally shows up here. It's not always increasing. All right. If I go to the next one, I go up now. So this one's going to have, going to the next element, this would be carbon. This would be ends with 2p2. And go to the next one, this would be 2p3. Now, why do you think it goes down again? So if I go to the next element, so this is 2p3 would have been nitrogen. So this would have been nitrogen. If I go to the next element that's lower here, this is oxygen. So this is a 2p4. Why would it take less energy, you think, to plug off oxygen's electron configuration, that last electron, than nitrogen? And I'm going to give you a hint. Okay. Half field, stability. Partial field, lack of stability, that makes this one that much easier to get off. And then the rest of them is we're putting electrons on more and more energy. And then now we've got this point. I got a noble gas. That's the greatest stability. That takes the most energy of anything. Once I go beyond the noble gas, go to the next one, huge jump down, and I repeat the pattern going back up. And then same, fill the noble gas, go back down, repeat the pattern over and over and over again. Okay? But these irregularities are due to partially filled orbitals. And the stability that comes with those. Is it a half full? If it is, that means stability. Okay, and that's where you get the little jumps up and down. Okay, here's one way to look at it. Here's another way to look at it. Here you can maybe see, this is the same data that's in the previous chart, but here now you can see the trends a little easier. So generally remember it where it's the largest. That's the way I tend to remember it. It's greatest for helium. As I go down a period or down a column, so like the noble gases, it gets less further and further out you go. Bigger shells to the onion, greater valence layers. Okay? Generally, going right to left is decreasing, but you have these little stair steps in here that occur at different places, and that's because of the half-filled places. So if we look at what's happening in particular going from the 2A to the 3A, and then again from the 5A to the 6A positions. So if we look at nitrogen, what's going on with nitrogen, its electron configuration was 1s2, 2s2, 2p3. And oxygen, we said, was 1s2, 2s2, 2p4. Okay, just comparing those two. The fact that this is the half full, and there's stability in that, that's the reason nitrogen is actually just a little bit more than the value is for oxygen. Even though the general trend's going up as you're going from left to right, because of the half-filled stability, that's where the little peaks come from there, or the sawtooth patterns that occur. We can understand this, that you get a sublevel that's half full, it costs more energy to break that guy up. Once you get that it's beyond half full, it takes less energy to break this guy up. So if you want to pull that electron off, it's easier than breaking up one of the three from the half full. Now, the question you may ask, if it's going to take one of these, which one? And the term that we use to describe that is degenerate. They're all equivalent energies. So in the P, there's P, X, Y, and Z, okay, and we would represent those with the M sub L of -1, 0, or +1. They're all equivalent. So it doesn't matter which one you take. It's going to lose one of those off, right? Okay, so if we look at what happens when we pluck that second electron off, and how does it change? All right, when we pluck the second electron off, it takes more energy to pull off the next electron. Why? Because now the effective nuclear charge has become much, much greater. So here's an example of sodium, and its first electron's ionization energy is, sorry, I said that backwards. Once you lose the, here's the first one. Here's the first one, highlighted the wrong one. It's a little bit less than 500. And then it gets to a noble gas. If you want to break up that noble gas, so once it gets to loses an electron off, it becomes a neon. If you want to pull the electron off of the neon's stability, it costs almost 10 times as much energy. Huge jump. If you want to pull a third electron off, it's almost 15 times as much energy. Okay, so there's a tax for pulling more and more electrons off. So you now got more protons than you've got electrons. The increases the charge. The outer electrons are now closer to the nucleus. That makes them harder to pull off. If you got two factors that are working against you. You're getting smaller, number one, and secondly, you got more charge. The greater the charge, the greater the attraction between the two. And we see this type of repetitive loss that goes over and over. So here's an example of what you see when you look at magnesium. So magnesium loses the first electron off, and that takes it to be just like sodium. But we know its goal is to be like that of the noble gas below it. So it really wants to lose that second electron off. So it doesn't take that much more energy to pluck the second electron off. But once it becomes like the noble gas, if you pull that electron off, it takes a load of energy. Okay, so magnesium 2 plus that occurs here, that's pretty easy to form. But if you wanted to mess up the magnesium 2 plus's electron configuration, it's going to take a ton of energy for that to occur. Goes back to the stability that occurs with the octet rule. So here's some, just a table that shows you some of the changes that occur in terms of successive ionization energy. So it's kind of broken up into core electrons, and then on the bottom, these are the outer shared electrons, or the valence electrons that we have. To pluck off the valence electrons, you'll see that in all cases, the numbers are significantly smaller than what it takes to pull out a core electron out of the system. So how many valence electrons does something pull off? Well, it depends on what charge does it want to do. Now, this is looking at the period 3 going across the periodic table, going from sodium all the way across to argon. When you get down to argon, even to pull off the first electron, there's stability there. It takes a lot of energy. Okay, but there are some things that use argon and form argon. It's not that it can't happen. You can take argon and get argon to kick an electron off to form the argon ion. One of the applications we use that for, and I've got one in my research lab downstairs, is to use an argon ion laser. All right, argon ion lasers are commonly used, and they emit light at 488 nanometers. They're commonly used for medical purposes. I use them in a technique called fluorescence, where we use a dye that attach it to a protein or something we want to visualize, and we can shoot it with a laser light that comes from the argon ion laser, and it glows, and we can look at that with a camera that sees it glowing. And with that, we can detect as little as 1 atom or molecule. Okay, it's the most sensitive detection that we have. Applications for other things that use argon ion lasers in medical purposes. Lasers used to cut tissue open. Frequently you use a CO2 laser or an argon laser. There's a lot of different ways that we look at that. Even though we think of noble gases, that's stability. If you pump enough energy into it, though, you can pluck that electron off. It's a lot of energy in terms of kilojoules per mole, but it's not undoable in systems. Okay, take the trends and organize these. So I'll let you, in a Thanksgiving mood, ask a partner. Ask somebody around. Get a group problem. Okay. Now, rate it. Make sure you read it carefully in order of decreasing ionization energy. Put the largest energy on the left, going to the smaller. You should be able to look at those trends. Where was it the greatest?
The order of decreasing them.
Okay. 1, 2, 3, 4, 4. Should have 22. Need 2 more. Survey says. Okay. So most predominant answer is C in this. So there was one thing that you can look at this that kind of gives you a hint that tells you what it is. And I heard somebody say it, and that is that flyway. Flyway. Okay, just move over here then. All right. So it's C. The thing that's the hint that you can see that's kind of the biggest is this is the noble gas. And noble gases always have the largest ionization energies. Okay? That was kind of your thing to look at in this problem to see. That's the clue for it. Whenever you do these standardized exams, you're going to have a question like this probably on the fourth exam. You're going to have a question like this on the final. Look for the one that's the largest or the smallest. That starts your trend out. Now on these, the way that when we write the exams, anything that didn't start with argon was called a distractor. It meant that it couldn't be anything else. Usually you're going to have a couple of distractors and you're going to have two that make sense. So probably if this were given on the standardized exam, there would have been two that started with argon, so maybe the other one would have went like this. Okay? But look for that type of information. It'll help you answer questions much quicker when you recognize that. And that's what you're looking for in these tables and these trends. Where's it the biggest? Where's it the smallest? Okay? Start that as one side or the other. Okay. Next thing we want to look at is a term called electron affinity. It is almost the opposite, but it's not quite the opposite of the ionization energy. Instead of losing electrons off, now it's an atom's want of an electron. It's the amount of energy that's released when an atom gains an electron. Again, we describe it in the gas phase, and it's how much energy is going to be given off when an electron is added to a system. Now, we define it as exothermic. Okay, energy is going to be released, but in some cases, when it's not favorable, it may actually be an endothermic process. So it's not always a negative sign for it. So if you look at things like the alkali earth metals and the noble gases, they're endothermic in terms of their process. The why? They're happy where they are. If you want to put an electron on them, it takes energy. Okay, it's not energy being released. And the more energy that's released in this, so the larger the EA, the electron affinity, the larger the electron affinity. So the energy is directly associated with the extent of the electron affinity in these. So the more negative that number is, the more an atom wants an electron. Okay, so with electron affinity, the trend that we see is that when we go to the alkali metals, it decreases as you go down the column, but not all groups do that. There's more irregularities with electron affinity going from the first to the second to the third period. Here's another one of these generally increases. It generally increases as you go across the period. And why? Because it becomes more and more negative as you go from left to right. More than anything else, this one's not an absolute rule. Typically, you see things that are in the 5A group have a lower activation energy because now you're getting this extra electron and it's going to have to be paired up with something. All right? When you look at things in the 2A and 8A family, they typically have very low because now the electron goes into a higher energy level or into a sub-level. It's going to the next layer up. So you've got something that's not a full orbital, or it's empty, and it can go into a place as either an empty P or an empty S when you go into the 2A or the 8A families. And the highest of any particular period is always the halogens. And that's probably the take-home message from this page. The halogen family wants electrons more than any other family going up and down the periodic table. These guys want electrons. So in redox reactions, that's the way that they're going to react. They're going to pick up electrons from something else. We use this as things like, we were talking about electrochemistry in my other class this morning with in chemical analysis, and we were talking about how we use chlorine, molecular chlorine in swimming pools to disinfect, okay, to kill bacteria. Because it will react with living systems and take its electrons from it to the point that it kills that organism. Okay, it's a very powerful mechanism. All of the halogens have a strong ability to work in that function, take electrons from it. So if anybody Boy Scouts, maybe Boy Scouts. Okay, so if you've done the Scouts or if you've done a survival class, I talk about how to go out in the wild and survive. You don't drink water directly out of a stream not very much. It's a last resort. You do something to purify it or kill biologics out of it. Okay, you pick up parasites. A lot of things can go wrong. I mean, if you're dying of thirst, you drink any water that you get. But if it's going to be continuous, what you need to do something to it is to sterilize that water. The best thing that you can do if you got a fire is you can boil it. Okay, the heat, you can kill things that are living in it. But in the absence of that long term, you can add a halogen to it. So like if you've got a 2-liter bottle of water, and if you carry some people that are survival freaks, carry iodine crystals. Because it's the halogen. Bromine's a liquid at room temperature, iodine's crystalline. And you take one small crystal, and it's got a low solubility, and you put it in that 2-liter bottle of water, and you shake it up when it's sitting there overnight, and it'll kill all the biologics in there. Okay? And you can actually refill that thing about 10 times before that one small crystal dissolves. You got one little bottle, you got enough iodine to carry around to sterilize all your water for an entire year. Okay? Also, in the event of a nuclear war, iodine's important as well. So iodine goes into the body, the mechanism in which the reason it's important in terms of a nuclear event. And during the Cold War, in the height of the Cold War, during the 60s and 70s, we thought that the Russians were going to nuke us. Everybody learned this stuff in high school. You take calcium iodine tablets. And why? Is because the iodine, your thyroid picks up iodine, okay, and processes that in the system. And you want to saturate the body with non-radioactive iodine so that from a nuclear fallout, one of the major isotopes that's produced from a nuclear explosion is radioactive iodine. And that radioactive iodine is readily uptake, whether it's from water or breathing in air by your thyroid, and it gets part of your biological system, and that induces cancer. So if you can outcompete it with an abundance of regular iodine, you can minimize the uptake of radioactive iodine. So that's another reason to have iodine available for you in your survival pack. So if you got the survival kit. So here's the electron affinities in a table. Again, here's where we see problems with it. It's just their trends are just not always absolute. Generally, as you go down, they get smaller. Okay, that's the general trend. All right. However, it doesn't always work. Okay, so negative 27, negative 43, that one got more negative, and then it goes down to negative 30. All right, when you go left to right, it even becomes more erratic when you jump at things like the 5A family. So it's negative 60, and this one is positive, negative 27, so negative 122, positive, negative 141, negative 300, okay, positive again. So it's hard to say what's happening with these. You literally have to look at it at an atom by atom. And where's it going to be in terms of electron configuration once it picks up the next electron? Is it a half full shell? Is it a full shell? Is there stability because of being half full or full? That's the thing that dictates the electron affinities. And the electron affinities, if we looked at the magnitude of these numbers, these are kilojoules per mole. Nothing in here is in the thousands, like the ionization energies were for the noble gases. So you can make things pick up electrons, right? It's harder to pull electrons off. Okay, the last part of the chapter here, in the last 13 slides or so we'll make it through this with no problem. They're looking at the characteristics we have of different things in the periodic tables and how the things that we've talked about with the electron structure relate to the physical properties that we have. So metals, if we think about characteristics of metals versus non-metals, these were our definitions. One of the things is that metals are malleable and ductile. Malleable means that they bend. Ductile means that you can reshape them without them breaking. The other extreme to that is being brittle. Okay, so you can take a metal and bend it. If you have a non-metal and try to bend it, it's crystalline and shatter like glass. They reflect light. Typically, non-metals are going to be dull surfaces. They're conductors of heat and electricity. Non-metals are insulators. They don't conduct heat or electricity. Most of them form oxides that are basic. are ionic. And if we look at what happens with nonmetals, they're acidic and molecular in terms of nature. So again, that goes back with anytime that you have a nonmetal and a nonmetal react. We talked about this in type of bonds it forms. Those are covalent bonds. That's molecular. When you have a metal reacting with a nonmetal, that's a transfer of electrons. That's an ionic bond that forms. And just recognizing that will help you answer so many things in chemistry. They tend to form cations. Metals do. Nonmetals form anions, or polyatomic anions, but they're negatively charged. So they, in reactions, they lose electrons. They're oxidized. What happens with nonmetals is they gain electrons and they become reduced. So if we look at metallic characteristics, so how much is a metal like that of a perfect metal? And the term we use to describe that is metallic character. Not all metals are equal in terms of those characteristics that are listed on the previous page. Some metals are more malleable and ductile than others. Some metals are better conductors than others and easier to ionize. One of the things that would make our life easier if we could produce a supermetal, or a way to have a supermetal that was a superconductor. So has anybody heard the term superconductor? What's that mean? Okay, a superconductor means that when electricity flows across it, which is the flow of electrons, there's no resistance to it whatsoever. Okay, so there's no energy lost by flowing those electrons across a distance of a wire. Okay, most things, even a piece of copper wire, which is a good conductor, if you go across 10 feet of wire, there's a certain amount of resistance to the electrons flowing across that wire. Okay, and that's called, we measure that in the amount of conductivity, typically measured in terms of ohms. You have a conductivity meter, or you had a digital multimeter. But there are some materials the electrons can flow across and there's no resistance. In fact, there's an example of one of these things. There's in this garden, whatever you want to call it, out your window. There's a research space our private has. There's a silver container out there. It's got a black top on it, kind of sitting out in the middle with vines growing all of it. Inside of it, there is a rare earth oxide that was made in the form of a magnet. And what happens is you would take that magnet, you would put it in liquid helium, and it would cool it down to 4 degrees Kelvin. And at 4 degrees Kelvin, that particular material, you put electrons in it, putting charge on it, they start spinning around. There's no resistance to those electrons spinning around. And they'll maintain that flow of electrons indefinitely, as long as you keep it cold. Right? And some of you have seen these little magnets that levitate. You've seen a demonstration with those in maybe a science class in high school. Those are superconductors. It takes liquid helium or liquid nitrogen for it to work. That's the best system. We lose so much electricity transferring it from the power plant, wherever it's made, to our homes. 50% of your electric bill is spent to heating the wires up. Okay, you're buying that electricity that's lost due to thermal heat, due to the ohmic resistance. If we could produce materials that were superconductors at room temperature, we'd make a huge jump in terms of efficiency. That's the big push in material science. Like that old magnet that's out there, it took that those materials had to be at about 10 degrees Kelvin. But that's a technology that's 30 years old. That's the reason it's out there in the garden. It's dead. Okay, because liquid helium costs so much now compared to what it used to. So then they started designing newer generations of conductors. So has anybody been to Six Flags Road, Mr. Freeze? Okay, so that one has a series. It shoots you off at a high speed, then turns you straight up, and then you come back down, right? That's Mr. Freeze. I got my ride. That's right. Okay, on it, you're on what's accelerating you is a series of superconducting magnets. There is a permanent magnet in the track down at the bottom, and those are superconducting magnets, and they energize different magnets in the car that cause those to repulse from one another. And you're being pushed by that type of repulsion. Today, that is being utilized in bullet trains. Okay, that's one of the places they're using that at. So like in Japan, there's a series of bullet trains that inside of a controlled environment, France has one as well. These trains are going 200 up to 300 miles an hour. Okay, and they're being propelled by the superconductor technology. When we get to the point where we can integrate these into things at room temperature, we will decrease our energy consumption by 50% at least. That's less demand on fossil fuels. That's better for the environment. There's a lot of we need to on this. Here's where politics comes into play. Everything good, there's a bad. The world's stakeholder of these materials that are being made are called rare earth oxides. Okay, so the rare earths are down here in the bottom of the periodic table, and the lower the transition elements, China has the world's stake on. China 2 years ago said these are a protected natural resource the rest of the world can't have them. So the cost of these things started to go through the roof. And now we've had other places in the world that quit mining them because they do it so cheap in China, have started to try to redo them. And political said, well, China exports a whole lot more than they import. Other countries in the world said, keep your semiconductors, keep all your other crap. And there was a really big trade war that was happening in the scientific community in the background, because you take out the feed from China, no Apple chips, no Dell computers. All those super rare earths were used to make all the stuff we did in technology. And China had to back down because practically the rest of the world said, you keep your rare earth and you keep all your other crap. And China had to release its hold on them. And now there's a supply of those for the world for some time. So that's just one example of how these metal characteristics, if we can engineer better materials, they're going to change everybody's lives. And these things are not figured out. I mean, science is continuously evolving and changing. The whole field of material science is just that. It's how do you put a new group of atoms together in a way that had never been observed with some property. Whether it's the design of an alloy to make a structure that's stronger, lighter, something unique about it that's needed, or a way to combine atoms in a way that makes a superconductor that could be used at room temperature and could be integrated in almost any electrical device. It's a bright future. It's just we have to come up with the technology to do it with. All right, metal character. How much metal character something has, it decreases as you go from left to right across the periodic table. So something that's the most metal, or the things that are over here, as you start going towards the non-metal, it starts to lose some of its metal characteristics. Okay? So if we look at the other trend we see is that metal character increases as you go down the periodic table. So lower and lower. The thing that has the most metal characteristics would be francium. Francium's radioactive, so let's not play with that one. The next thing's cesium. Okay, so here's where if you want to go to the corner of the table where it's the largest metal character, it's here. So if you go to the thing that's the extreme non-metal, the other side, you're up at helium. That's the most non-metal character. Okay, that's the trends that you have. And when you get to something that's some of these odd metals, things like mercury, mercury's got some mainly metal characters, but it's not a solid. It's the only metal that's not a solid at room temperature. And it's especially these ones that are right in here in the middle that are in the green, the ones that we call the metalloids. Today, they're the ones that kind of have the dividing lines between is it a metal or is it a non-metal. This guy in particular, because it's used in the integrated circuit. Okay, without that, your cell phone and the technology in your cell phone without an integrated circuit would be the size of this building. If it used 2 base transistors in your cell phone, each transistor is the size of a small light bulb, and there's 1 billion of them in your cell phone, the heat that would get it off would have to be the size of this building. That's what early computers were. Okay, but integrated circuits and the ability to produce refined silicon have changed that technology, made life much better for us. Everything that's in here, these are the things that are inside of your integrated circuits to make them work. You want a faster, smaller computer, they're all using those elements. That's the topic of inorganic chemistry and the great things that we're doing. And a lot of that stuff happens right around here. Has anybody drove from Tishomingo to Sulphur? Anybody from that area? So when you make the turn, if you're going, if you go from, you'd actually go to Arabia, then go north, and you'd make a left and go west, and you cross some railroad tracks, and there's always some white-looking powder laying around. And if you're in the winter, when there's no grass around, if you look out in the fields, it looks like salt laying everywhere on the ground. Okay? There's a plant there called U.S. Silica, and it produces, or mines up out of the ground. It doesn't produce. They do clean it up. But it's silicon oxide, sand. But it's not sand like you see at the beach that's kind of brown looking. This stuff is glowing white. It's the purest silicon dioxide in the world. And they take this stuff, they don't take this and manufacture your cups that you're going to use at a glass at Walmart. They take this stuff and send it all over the world and refine to make optics out of. Nice optics. Okay, 90% of it's shipped to Germany, because Germany makes some of the best optics in the world. Well, 90% goes between Germany and Japan. Japan does a lot of great optics as well. But just the ability to have this element so readily available, that's the reason Texas Instruments has a plant here. That's the reason if we look at Cardinal Glass that manufactures glass, they have a plant here because we have an abundance of this mineral, the silicon dioxide, close to us. All right, so your trends in the periodic table, again, I don't like the way the authors set their things up. I think it should be that it increases as you go this way. So here's where it's the greatest. Greatest mineral characteristic is at the bottom left of the periodic table. Okay. So the trends that we have in terms of some of the families in the periodic table. So we know when we go to the alkali metals, so 1A family of the periodic table, so 1A's far left-hand side, that the atomic radius increases as you go down, more shells to the onions. The ionization energies increase as you go down. Okay, so it becomes easier to pluck an electron off. They have low ionization energies because they want to get rid of that one electron. When they do, they become like a noble gas. That makes them very good reducing agents because they're easy to oxidize. We never find them in nature in their neutral form. You never dig up a chunk of sodium and it be elemental sodium. It's always in the form of sodium plus 1. When we want elemental sodium, we have to take that and process it back in a chemical reaction, typically electrochemistry, to convert it back into elemental sodium. They're very, very reactive. If you take a chunk of elemental sodium, throw it in water, it explodes. It gives off hydrogen gas very rapidly, and it produces enough heat that ignites that hydrogen to blow up. Okay? They reduce with nonmetals to form salt, table salt. They're typically very soluble in water. We can find an abundance of these things by just letting some seawater evaporate out. Okay, so anybody that's dealt with the residue from seawater, it's typically alkali metals that are the most of that. Their electron affinities decrease as they go down the column. Their melting points decrease as they go down the column. And they all have very low melting points for metals. Okay, so if you take something like cesium is actually a liquid at room temperature. Going up just a little bit, rubidium, if you hold it in your hand, 37, it'll melt. Turn it into a liquid. Potassium, you've got to heat it up to about 70 degrees. Sodium's melting point is about 100 degrees Celsius, but even at room temperature, it's soft as butter. I mean, you literally take a block of sodium metal, you take a butter knife, and you cut off the chunk. And it usually comes in like a stick that's like a margarine, like a 2-centimeter stick of whatever length. And you have to keep it from oxygen and water, keep it immersed in typically mineral oil. So we pull some out of the container, slice off our little piece of it, put it back, and then we put in some mineral oil, keep it away from water. All right. Densities increase going down the periodic, going down a particular column, except for potassium. And typically that means that the greater mass that you have, the mass increases more than the volume, so the density is going up. So all we said the characteristics they all have in common is they all have one valence shell electron. Their radiuses get larger, their ionization energies get smaller, so the ionization energies are smallest at the top, and their densities become larger and the melting points become lower. So the melting points are greatest for something like lithium. So sodium is around 100 degrees. And if we look in terms of the reactivity, okay, lithium, if you throw some lithium in water, it'll fizz. It'll give off hydrogen gas, but it doesn't produce enough heat to ignite that hydrogen gas. If you threw some sodium in water, it's going to ignite that gas, and if the gas can build up, it can be a significant explosion. However, if you drop some potassium water, the reactivity gets greater than greater. It's going to blow the beaker up type thing. It's a very, very exothermic reaction and gives off a tremendous amount of heat. All right, going to the other side of the periodic table, the halogens. So when we look at the halogens, what we have with their trends is that their radius is increased as you go down the table. Their ionization energies decrease as you go down the particular column. They're the ones that want the electrons most, so they have high electron affinities. That makes them good oxidizing agents because they're easy to reduce. They themselves are also very reactive. You never find elemental fluorine, chlorine, bromine, or iodine in nature. They're always found reacted as salts. So whenever we make molecular iodine, like we put on our arm to sterilize it, if you gave blood and got your bonus points, that was a form of iodine. We used to use molecular iodine. Okay. Now they've switched to it's a iodine bound to a, I'm trying to think, it's hexafluoroethanol or something like that. It still has iodine on it, but it's an organic material because some people are allergic to iodine. Get it, so it's not as allergic reactions occurring. But we just don't find them in nature in the uncombined forms. They react with metals to form salts, and typically they're also going to be soluble. And again, our abundance of these things is seawater. I mean, there's literally tons and tons of finding these. So where do you think we get our salt from? So our salt shaker salt. Where does it come from? Say again?
Is it like the,
Okay, so if you've been to Utah,
Okay,
yeah, Great Salt Lakes, where there were inland lakes and the water evaporated, and the water evaporated off, you left with salt. They have deposits that are hundreds and hundreds of feet thick of these alkali metals combined with halogens, and that's where we get our salt that goes in our salt shakers. They literally come out with a bulldozer, pull some up, crush it into the little pieces, and run it through a dryer. Sometimes they'll wash it with a little bit of water if it looks muddy, tire tracks, or some diesel spilt on it. So that's exactly what they're doing. Nothing else other than that to clean it up. And that's what you're eating. In nature, animals need these things. So farmers put out salt blocks for their cattle. If you want to attract the deer, you can put out a salt block and the deer will come get it. Animals in nature know where minerals are. The animals in the wild know where the minerals that have high salt contents, and they'll walk by occasionally and they will lick that rock. Sounds crazy. Go sit out in deer woods and watch what happens with a deer. Bow hunt where the deer sits 20 yards beyond where you can shoot, and you get to watch them for 8 hours straight. Just a little bit further, and just see what animals do in nature. Okay, they're constantly aware of their nature and their surroundings, and they have to have this content. That's one of the problems that animals that are grown in restricted cages, okay, whether it be cattle or pigs or chickens, those are our protein sources we eat. But if they're not allowed to go out in nature and lick the rock or eat the grass that has the minerals in it, if they're given a synthetic diet, they have to be given supplements or they'll get diseases. Okay, like example, selenium. Selenium is found in nature, and anybody that's exposed to dirt and grass and everything else picks up plenty of selenium. But there are certain places on Earth where there's not much selenium. In China in particular, there was one village where they had this disease they discovered in the 1930s. They couldn't figure out what was going on, and everybody was dying with these similar characteristics. And they started doing testing, and they started looking at what's in nature. Well, this was a population of people where everything they were eating was grown in this community. Okay, they were self-isolated, and they were looking and it was selenium depleted. So once they just simply gave these people some selenium supplements, the disease completely disappeared. Okay? Everybody that takes, let's say, one of the things I'll tell you about a multivitamin, all of us are exposed to different things. So we're typically pretty good, but things like pigs that are grown in these farms like Tyson's, chickens where they're not allowed to go out in the environment, they stand on concrete their entire lives, they have to have supplements. Okay? They have to be able to pick up these elements that they normally would get in nature. So the halogens get more reactive as you go down the column. They'll react with hydrogen to form acids. Okay, strong acids in particular for most of them. The only example is HF, hydrofluoric. Their melting points and boiling points increase as you go down the column, and their densities increase much like that of the alkali metals. So if we look at their common thing they have 7 valence electrons in all of these guys. They get bigger as you go down. Their ionization energies are the biggest at the top, so they get smaller at the bottom. Their melting points get bigger as you go down, and their boiling points do as well, and they're also their densities. Now, they're one of the families that can be found in all 3 phases. So what I mean is that at room temperature, these are all isolated containers of these substances. Bromine is in a liquid state, so it's a liquid. Chlorine is a gaseous state, and iodide is in a solid. So it can be a solid, liquid, or gas, depending on which element it is in that family. And that's pretty unique. Most of the other ones are either all solids, or all liquids, or all gases. The halogens are the ones that are more mixed up. So some of the reactions that occurs is that alkali metals are very easily oxidized to form +1. So if you mix it with a halogen, what happens, the halogens want to be reduced to form the -1, and then you form an ionic compound that's attracted to each other. That reaction is very favorable, and it gives off a tremendous amount of energy. Okay, so here's an example of taking some sodium and throwing it in a container with some chlorine gas in it. So you open it up, throw it in, put the petri dish back on, the thing looks a lot like a light going off, and at the end of it, there's going to be sodium residue. Can't see that color. There's going to be sodium residue or powder all along the edge of this. That would be table salt you could just eat. Okay, so it's a very, very exothermic reaction. Today, this is one of the ways that we're storing energy in systems. Most of you, this is your friend. Because in the olden days, when we walked to school uphill both ways in the snow, our batteries on our cell phones had about an hour talk time. And you literally, if you just left your cell phone on with the old battery technology, you had at the most 10 hours of battery life. And in 10 hours, your device was dead. But they've changed the different batteries, and now we have our lithium-ion battery, which is one of the most energy-dense ways that we can store batteries. It's changing the way that we do everything. Your cell phone now, it depends on how much you spend on your cell phone. I charge my cell phone once every couple of days. Okay, and if I'm not using it, I can go 4 days. Because I don't even like to answer phone calls. Okay, so I don't like cell phones anymore. They've changed the way society interacts, and I don't think it's necessarily always in a good way. But the positive thing that we see, things like, you think that the lithium-ion battery has anything to do with your car? The biggest plant that's being built in the world right now has to do with automobiles and lithium-ion batteries. What is it? It's the new Tesla plant. The Tesla plant, they're manufacturing lithium-ion batteries. The focus of that plant is to make lithium-ion batteries for the world. Okay, it's the largest plant in the world. The energy density, you'll be able to plug your car into the wall, and instead of putting $50 worth of gas in it to be able to drive 300 miles, you'll be able to put $1 worth of electricity in it. Okay, and they're making the S-type Tesla car that's coming out next year to be produced is going to be in the neighborhood of $40,000, affordable.
Now, they have already got some $100,000 plus ones that are available, but the S-Type, the new one, absolutely has the ability to revolutionize the automobile industry. If they can produce it and it stays effective as they think. I mean, because now you don't have to worry about gas. Okay, changes your world. All right, there's just a slide or two left. We'll finish this up on Tuesday, and we'll do our problems at the end of the chapter.
Yeah.